finally we came up with this mathematical framework for the Perceptron model. Now we'll see a few examples how we can learn this weight hyperparameter, which is a weight for the Perceptron. Usually this hyperparameter are learned through optimization based algorithm like gradient descent, Adam, and much more. Through backpropagation we'll be looking later in this lecture series. Okay, so for to understand more in depth, we'll be looking at how we can learn this weight manually, so that we can get more intuitive way of this learning algorithm. Okay. So let's first learn this weight, so that we can make this perceptron to work for the OR logic. Okay, so if this is a perceptron, and let's assume we have x1 and x2 as input, and we'll get y, which will denote whether this neuron will fire or not. Okay, so we'll be designing this weight so that this y is y fires and doesn't fire as per the OR function. Okay, so let's see the truth table for the OR function. Okay, and this is the y. This will 0 0. These are the possible input of the for the two inputs. And for OR function, okay, so if this is OR function, then it will be 0 1 1 and 1. Okay, so we'll see the perceptron for function, perceptron in perspective. Okay, so if we look at this function, this can be expanded. So we'll see it how it can be expanded. Like it's a okay, so we will just see the expansion of this person. Okay, so if I equals to 0 to n, so this is the perceptron model. Okay, so we'll just see the expansion. Okay, expansion for this expression. Okay, so this can be expanded as it can be expanded as W0 for the two inputs. Okay, we'll just be looking for the two inputs, x0 plus W1 x1 plus W2 x2, and we know the x1 is 1, right? So it will be just x W0 plus, and this can be again rewritten as or let's leave it like this. Okay, W1 x1 plus W2 x2, or it can be rewritten as like summation of y equals to I equals to 1 to 2 wi xi. Okay, so let's leave it like this way. Okay, so let's erase this one. Okay, so now so it will be 0. This neuron won't fire. Okay, so this neuron won't fire at this condition, right? So it will be smaller than 0. So we'll use this function. Okay, so W0 W1 x1 plus W2 x2 is smaller than 0, right? It doesn't fire for smaller than 0, and rest of these all are the neuron will fire. So for all of these cases, we'll have W1 x1 plus W2 x2 is greater than equals to 0. Okay, so now we need to learn this weight. Okay, and we don't know exactly what this what would be the exact value, but we'll come up with some approximate values. Okay, so and also, like, for each of this expression we'll be like substituting for these values. Okay, so if we for this input values we'll be getting So okay, so we'll be naming as like 1, 2, 3, 4. Okay, for easy, for our own easiness. Okay, so so 1 will be, okay, so if we substitute this values x1 and x2 on this expression, then we'll get like w naught plus, this is 0 0, and that's like going to make smaller than 0. Okay, this is one of the condition for the OR gate, OR logic, for this perceptron to work for the OR logic. Okay, so if we substitute 0 and 1, so we'll get okay, so for the expression this is the 1, and that's going to be like, this will be 0 and this will be 1, so w naught plus w2 is greater than 0, and the other condition is, okay, let's substitute this one, then that's going to make w2 plus w1 is greater than 0, and fourth one is w naught w1 plus w2 is greater than 0. Okay, so now we have to learn this learn the value for this, what exactly this w naught, w1 and w2 would be, so that our perceptron will work as a this will work as an OR gate. Okay, so I mean, this is my approximation. You can come up with your own approximation. So we don't know the exact value for this parameters, so just for some understanding, I'll be like assuming, okay, w naught equals to 1 minus 1. Okay, this is just my approximation. Okay, so you can put it anything, but it has to fulfill this condition. Like, you cannot violate this expression and assume these values. Okay, so w2 equals to 1.1. So that's okay. So now graphically, let's see. Okay, so let's graphically look at, okay, graphically observation. What would be the observation with these values? Okay, this is x1 and x2, and this is 0 0, 0 1, 1 0, this is 1 1. Okay, so if we plot I mean, if we substitute these values, okay, w naught, okay, if we substitute this w naught, w1 and w2, and okay, in this expression, if we substitute these values, and let's keep it x1 x2 as the variable, then we'll be getting something like minus 1 plus 1.1 x1 plus 1.1 x2 equals to 0. Okay, so it should be greater than 0 because we just want the boundary where our neuron will fire, so that's going to be greater than 0. But to get the approximate value, let's make it the substitute, and if we want to plot this expression on this graph, then we'll get something like it won't exactly cross because it's greater than 0, so it will be, okay, it will come somewhere like there. Okay, just a little bit lower than 0 1 and 1 0. Okay, so this is the boundary which has been formulated based on this weights, but the possible boundary solution for different values of the weights might be among any of these. It can be like here, anyway, but it cannot go beyond this line. Okay, so these are all the possible values. So these are all the possible solution for the decision boundary. Okay, so this is the person where our y equals to neuron will fire, and these are the portion. Okay, for this boundary, this is the portion where our neuron won't be fire. Now let's see the example for the AND function. I mean, learning the weights to make the same perceptron. Okay, same perceptron work as a AND gate or AND function. Okay. So again, we'll assume the same perceptron. Okay, with 2 inputs, and the and y will be the boolean. Will have a boolean value indicating whether this neuron will fire or not fire with different values of this x inputs. Okay, to make clear, so only these are the one of the inputs, right? So I mean, this is like W1 and W2, which we are running, and there there is one more W0, as we have seen before. So where exactly is this coming from? So for every neuron or every perceptron, so there is one more input which is called a bias. Okay, so we can we have indicated that bias as x0, whose value is 1, and its weight will be W0. So that's why it has 3 inputs. Okay, so there is always one extra input the input for the every neuron, which is known as bias. Okay, so again, let's rewrite the truth table for the AND function. Okay, so these are the possible inputs for the x inputs. Okay, for AND gate, this is going to be 0, 0, 0, and 1. And we'll be using the same expression. Okay, I mean, not this one, the expanded one. Okay, this one, we'll use the same, and then we'll substitute this value. Okay, so let's substitute x1 on x2. So that is going to make W0. So what we can do is, and this is going to be smaller than 0, right? So wherever there is 0, that's going to be smaller than 0, because that is the, 0 means like neuron doesn't fire. So that's when this is the condition, like when neuron doesn't fire, it's smaller than 0. Okay, so let's substitute M0 and 1 in the same expression. Then we'll get W0 plus W2 is smaller than 0. Similarly, W0 plus W1 is smaller than 0. Okay, so for this, we'll be getting W0 plus W1 plus W2 is greater than 0, because this is the condition which neuron will fire. Okay, again, let's assume the different let's approximate, because we cannot come with the exact value, because so that's why we are using optimization based algorithm, which will exactly come up with the most nearest closest value for this weight. Since this is a manual way, so I'll just approximate. You can approximate yourself as well, but this condition has to be met. Okay, so let's assume like W0 equals to -1, and the thing is, I'm not as approximating this value more randomly, because I have already checked with these constraints, like if these values are like meeting these constraints or not, and exactly they are meeting. Like so one way, how can we check if these values meet this constraint? So what you can do is we substitute this value in this expression, and if this condition are met, then that's fine. If it's violated, then this expression, this weights cannot be taken into account. Okay, so I have already checked that before, so everything meets this constraint, so we are good to go with it. Okay, so again, let's see the let's see the graphically, let's see it graphically. So hopefully just plotting this x1, x2, this is 0 0 0 1 1 0 and 1 1. Okay, for this expression, okay, again what we'll do is we'll keep x1 and x2 as a variable, and then we come up with some expression so that we can see like what exactly this means more in a graphical way. Okay, so we can just make it like -1, because w0 is -1, plus w1 is 0.9 x1 plus 0.9 x2, and this is again like it should be greater than 1 0, indicating that the condition for the firing of the neuron. Okay, this is condition for firing of the neuron. But to approximate that, let's keep it as a equals to, and that equation is going to come at this location. Okay, little bit above the okay, so this is -1 plus 0.9 x1 plus 0.9 x2 equals to 0. Okay, and again it like if we approximate with different values for this weight, then we are going to come up with some different boundary equation. So this can be this equation, this, or any of these, but it cannot cross this point, and also it cannot exactly pass through this point, so it can be just near to that point. Okay, and I think I have like forgot to mention earlier, for OR gate this doesn't exactly pass through this point. Okay, so it goes a little bit closer to that point. So I mean, these are the only possible boundary solution for OR logic to make that perceptron work as OR gate. Okay, so if we look at this distance boundary, then this is the area where our neuron will fire, and this is the area where our neuron won't fire. Okay, so these are again the possible boundary. Okay, let's say possible solution for the distance boundary. In order to make our perceptron work as a OR logic. Okay, so I think that's all for today. Thank you.